This is the first video of kinetics, and what we're going to focus on is how to draw and label a potential energy diagram. So to start with, it'd be good if you could take out a piece of plain paper and make this pretty big. You could take up the entire space of the paper. We're going to draw what we call a potential energy diagram. So you can go like this, make a big curve and go down. And what we're going to need to do is label various points on the graph, and we need to know what they represent. So just like the heating curve, where we had to be able to understand where you're a solid, where you're a liquid, where you're a gas, we're going to be doing something similar with the potential energy diagram, where we're going to draw labels, and we need to know what they correspond to. So if we look at our y-axis, we see we have potential energy. So anything that starts on the bottom of this potential energy diagram, so for example here, we're starting at the bottom of the graph. Here, here, or here, anything starting on the bottom is measuring some type of potential energy, because that's what our y-axis is. So let's label A. We'll label B and C. What the potential energy diagram is showing you is over here on the left-hand side, these are your reactants. And we're following the progression of a reaction. Getting to the top of the hill has a special name. This is called the activated complex. Kind of like a transition state, and coming down and forming products. So we're looking at the reaction pathway. So letter A would represent, since it's starting on the bottom of our diagram, the potential energy, which I'm just going to abbreviate PE, potential energy of the reactants. B starts also on the bottom of our chart. That's going to measure the potential energy of the activated complex. C also starts on the bottom, so it measures the potential energy of, what is it going to? The products. Now we can draw in a new line from the reactants to the top of the hill. We'll call this D. D is going to represent what we call the activation energy. Activation energy is how much energy you need to get the reaction started. Right. Like when you activate a credit card, it could start working. So energy needed to start a reaction. On the opposite side of the curve, over here where we have our products, we can make a line from the products to the top of the hill, and that will represent, we'll call that E. E will represent the activation energy for the reverse reaction, meaning if we were to go products following a pathway going back to reactants. So that's what we call the reverse, going right to left. The forward reaction is D. We always assume forward unless stated that we're looking at the reverse. So D is the forward activation energy. E would be the activation energy for the reverse reaction. My diagram is starting to get messy, so you could see what's going on. I'm just redrawing it. You can keep going on yours. I just want you to make sure that you're seeing all the lines that I'm seeing. So next what I want you to be able to draw is in between, we have our reactants here, and you have your products here. This line, sorry. I'm going to make a straight line. This space in between them is known as delta H, which you've already looked at a little bit on table I. It's also known as heat of reaction. And it's equal to the potential energy of the products minus the potential energy of the reactants. So let's say we would put numbers in our graph. Let's say this represents 50, this represents 100. The delta H is equal to the potential energy of products minus the potential energy of the reactants. So if we were to assign or plug in the numbers that we have, here the products are at 50, and the reactants are at 100, so 50 minus 100, you would get a negative 50 value. Negative 50 what's the significance of the fact that it's negative is that it's an exothermic reaction. So this diagram is an exothermic potential energy diagram. So if I wanted to get an endothermic potential energy diagram, and delta H is products minus reactants, we'd have to draw it slightly different. So this is a picture of an endothermic potential energy diagram. On the reverse page, I would make this nice and large, redraw it. If we were to put in numbers, let's say again I use 50 and 100, our delta H here would be products, which is 100, minus reactants, which is 50. So delta H is 100 minus 50. I get a positive delta H value. Positive delta H indicates an endothermic reaction. Or also as a trick, I remember that endothermic ends on a high note. You may have heard that in like music class or something, that you end on a high note. So we're going to end on a high note. It's going to indicate that it's an endothermic potential energy diagram. The lines will all match up and correspond the same way. So here, this would represent the potential energy of reactants. We have the potential energy of the activated complex and the potential energy of the products. And then this line would correspond to activation energy and reverse activation energy. Tomorrow we'll do some practice in class looking at what each line represents on each curve.